All right, welcome back. Today, we are diving into one of the coolest ideas in all of AI, systems that can literally teach themselves. I mean, imagine an AI that you can just point at a massive, chaotic pile of data and it just finds the hidden patterns all on its own, with no human teacher in sight. Let's get into it.
And that really brings us to the big question, doesn't it? Can a machine really look at a super complex set of data and just make sense of it by itself? Well, it turns out the answer is a resounding yes, and the whole process is called self-organization. It's less about programming a bunch of strict rules and way more about creating the perfect conditions for learning to just sort of happen. So here's how we're going to break it down. We'll start with the big idea, this whole concept of learning without a teacher. Then we're going to look at the simplest way to do it, a model called the winner-take-all network. After that, we'll see what happens when we give it just a tiny bit of feedback. And we'll wrap it all up with these incredible things called Kohonen networks that can create actual maps of data.
All right, let's kick things off with that core principle. How on earth can anything learn without a guide? Well, this is kind of the magic of what we call unsupervised learning, and honestly, it's the foundation for everything else we're about to explore.
So what is a self-organizing system? You can think of it as a network of artificial neurons that learns through competition. So imagine you show it, thousands of pictures of animals. Instead of you telling it, this is a cat, this is a dog, the neurons themselves compete to become the expert. One neuron might basically raise its hand and say, hey, I'll handle all the images with pointy ears and whiskers, and it becomes the cat specialist. Meanwhile, another one becomes the dog specialist. They create their own internal prototypes of what a cat or dog is just by observing.
And what are these things actually good for? Oh, a ton. These systems are absolute workhorses. They're amazing at clustering, automatically sorting your customers into different buying groups without you having to define them. They can take massively complex data and just simplify it so you can actually see the big picture. They can find the perfect prototype of anything, really, and they can tell you exactly how similar a new thing is to all the other stuff it's seen before. Super powerful stuff.
Okay, so let's get into the nitty-gritty with our first model, the winner-take-all network. This is pretty much the most basic, bare-bones way a machine can learn completely in the dark, or blindly, as they sometimes say.
So how does it work? It's actually surprisingly simple. First, you show the network a new piece of data. Then, all the neurons basically look at it and ask themselves, who here is the most like this new thing? The one neuron whose internal settings, its weight vector, is most similar, wins. That's it. It's the winner. And what's the prize? The winner gets to tweak itself to become even more like that piece of data it just saw. Now do that thousands and thousands of times, and you start to see the neurons naturally drift toward the center of different groups in your data. It's awesome.
And really, this quote just nails it. It's a pure numbers game. The network isn't thinking, it's just calculating distance in a mathematical space. The neuron that is mathematically closest to the new data point gets the prize. It gets to learn. That is the entire rule. And it's pretty incredible how much order can emerge from such a simple idea.
Okay, but this brings up a really interesting problem, right? What happens if a neuron, just by random chance at the beginning, starts out so far away from any of the real data that it just never wins? It never gets picked for the team, it never gets a chance to learn, so it just sits there, completely useless. So, how do you fix that?
Well, the solution to these so-called dead neurons is actually pretty elegant. Instead of starting the neurons off with totally random out-there values, you just give them a head start. You initialize them using some of the actual data you're about to train them with. It's like instead of having some runner start the race a mile away from the track, you put everyone right on the starting line. It gives every neuron a fair shot at winning and actually learning something.
Okay, so far our network has been learning completely on its own. But what if we give it just a little bit of help? Let's bring in the next level of sophistication where we basically add a referee to the competition.
This slide really shows the key difference. On the one hand, you have the purely unsupervised model we've been talking about, where the network has no clue if it's right or wrong. It just organizes. But with reinforcement, we add a simple feedback loop. After a neuron wins and classifies something, we just tell it, yep, you got it right, or nope, that was wrong. And notice, we're not giving it the correct answer, just a simple thumbs up or thumbs down.
And this is where that feedback becomes so powerful, because it completely changes the learning rule. If the winning neuron gets it right, we do what we did before. We pull it even closer to that data point, reinforcing that good decision. But, and this is the new part, if it's wrong, we penalize it. We actively push its weight factor away from that data point. It's this simple dynamic of attraction for good answers and repulsion for bad ones that makes the learning so much more accurate. All right, now for the grand finale, and maybe the most powerful model of them all, the Kohonen network. You'll also hear it called the self-organizing map. And here, we're going to shift from pure competition to something that looks a lot more like collaboration. The goal isn't just to group data anymore, it's to create a literal map of it.
So what exactly is a self-organizing map, or a SOM? Okay, picture this. Instead of our neurons just being in a big random pile, imagine they're all arranged neatly on a 2D grid, just like squares on a checkerboard. Now, when you show the network a piece of data, and one neuron wins, here comes the magic. Not only does the winner get to learn, but its immediate neighbors on that grid get to learn a little bit too.
And this right here, this is the secret sauce of Kohonen networks. This is the big aha moment. We go from every neuron for itself to a full-on team effort. The neurons are no longer just independent competitors, they are related collaborators. And it's that relationship, based on where they are on the grid, that allows the network to preserve the hidden structure of the data and form a coherent map.
Now, this whole collaboration thing is controlled by something called a neighborhood function. The best way to think of it is like dropping a pebble in a pond. The winning neuron is where the pebble hits the water. It makes the biggest splash, it moves the most. The neurons right next to it feel a really strong ripple, so they move quite a bit too. And the neurons farther away, they feel a smaller ripple, so they move less. This function actually starts out really big, influencing the whole map at once, and then slowly shrinks over time to allow for more fine-tuning.
So when you first set one of these things up, the map is a total mess. The neuron settings are all random, so their picture of the data is completely chaotic. There's no order, no structure, it's just a jumbled, tangled mess. But then, after thousands and thousands of rounds of this winner and neighbors learning process, something amazing happens. The network organizes itself into this beautiful, ordered map. Now, similar data points activate neurons that are physically right next to each other on the grid. It has taken the high-dimensional chaos of the original data and flattened it out onto a 2D map that a human can actually look at and understand. It's incredible.
So, let's do a super quick recap of what we've covered. Self-organizing systems are all about learning through competition. The simplest ones are totally unsupervised, where the winner is just the neuron that's most similar to the new data. We can make them better by adding a simple feedback signal. Reward the right answers, penalize the wrong ones. And finally, these amazing Kohonen maps created ordered, visual maps of data by letting the winner's neighbors learn together as a team.
Which really leaves us with one final, fascinating thought. These systems are incredibly powerful tools for finding structure where our own eyes just see chaos. Everything from customer data to genetic sequences to signals from deep space. So it makes you wonder, right? What hidden maps of our world, of our society, maybe even of ourselves, will these systems reveal to us